In the previous session, we have seen the basic architecture of convolution neural network, which is also called as CNN, the layers and the neurons available at each layer, and how the pipeline, the CNN pipeline, is made up of. Now, for the today's session, we will be looking at the AlexNet. This is like the it is a 2012 architecture that proved the deep CNNs to dramatically outperform every prior method and effectively launched the modern deep learning era. So everything we have studied so far was the convolution, parameter sharing, pooling, the basic pipeline. So all of it existed in some form before AlexNet. Then what is AlexNet? What AlexNet did was prove conveniently and publicly that scaling these ideas up with the enough data and enough compute actually works dramatically better than anyone had demonstrated before. So AlexNet has boosted the performance of CNN. Moving ahead, we'll see the little historical context of this AlexNet. Before 2012, image classification, it was mostly relied on hand engineering features like SIFT and HOF, fed into the traditional classifiers like super vector machines, support vector machine. In this older paradigm, human researchers would design by hand a mathematical procedure for extracting meaningful patterns from an image and deciding in advance what counts as a useful feature. And then a separate, simpler classifier would be trained on top of those fixed and designed features. So this worked reasonably well, but had a hard ceiling. The reason is because no human design feature set could ever be as rich or as well adapted to the actual data as a set of features the network learns on its own. So that was the history of this AlexNet. But after this 2012, in the ImageNet competition, ILSVRC 2012, which is AlexNet, built by Hinton, and it is won. This competition is won by an enormous margin over every other method in the competition, reducing the error rate by a huge amount compared to the next best approach. So, which was still using the handcrafted feature. So, this was the turning point. It proved that the deep convolutional neural networks trained using GPUs and could dramatically outperform every older approach, essentially by learning the feature extraction process itself directly from the data instead of relying on the human intuition to design it. That was the advantage of from what we have got from this ImageNet competition. So that single result is really what launched the modern deep learning era we are still in today because it convinced the broader research community that investing in deeper network, larger data sets, and more compute was the right direction to pursue on. So that was all about the history of AlexNet. Let's move to the AlexNet introduction, done in a layer by layer manner. In these, we will see the actual AlexNet architecture. So the input is 227 by 227 by 3 image, right? So the layer 1 is a convolution with 96 filters of size 11 by 11 and stride 4, producing a 55 by 55 by 96 output, followed by a max pooling layer that brings it to 27 by 27 by 96. Now, if you notice, this first layer uses a large filter, right? 11 by 11 and a large stride that is 4. This is this was a deliberate design choice to quickly reduce the spatial size of the very large 227 by 227 input while still capturing broad low level patterns like age and color blobs in that particular first layer itself. So I hope you have understood this first layer. Now we'll move to the layer 2. In the layer 2 is a convolution with 256 filters of size 5 by 5, padding of 2, giving a 27 by 27 by 256, followed by another max pull down to 13 by 13 by 256. So we have noticed the number of filters in the increasing, filter size is increasing while the special size is shrinking. So which is a very common pattern in CNN design. So as we go deeper, we trade special resolution for a richer set of the feature channels. So since a deeper layers need to represent more complex and more varied patterns. Now then after this, there comes a layer 3, 4, 5. I hope you all are able to see this layer 3, 4, 5. So in a convolution in a row, so we have 384, 384, and 256 filters respectively, all size of 3 by 3 with padding of 1. So keeping the special size at 13 by 30 throughout until a final max pool bring it down to 6 by 6 by 256. So starting three convolutional layers back to back without pulling in between, as AlexNet does here. So let's the network build increasingly the complex features at the same spatial resolution before finally downsampling again. Then from there, we have three fully connected layers, two layers of 4096 units each, and a final output layer of 1000 units with the softmax corresponding to the 1000 ImageNet classes. So by this point, the network has converted the original spatial image into a rich, abstract, non-spatial vector of features. And the fully connected layers job is simply to combine those abstract features into the final classification decision. So this is how the AlexNet architecture is explained in layer by layer manner. I hope you are clear with this. So first we have the convolution layers, and then we have these fully connected layers at the end. So two layers of 4096 units each, and final output layer is of 1000 units with the soft max. We are able to see it as the layer 8. And then which gives us the 1000 classes as the output at the end. So the network has converted the original spatial image into a rich abstract non-spatial vector of features, and the fully connected layers job is simply to combine those abstract features into a final classification decision. That is done at the layer 8. Let's move to the pipeline of the AlexNet. So going down, and then we have the AlexNet as the pipeline. So in this pipeline, here there is some same architecture shown as a flow. So which is easier to hold in our head, right? So input, then convolution 1 plus pool 1, then convolution 2 plus pool 2, then the three stacked convolutions, convolution 3 through 5, then pool 3, and then two fully connected layers, and finally the softmax output. Whatever we have seen in the layer by layer manner, the same we have represented as a pipeline over here. So let's verify the first layer's output size using our formula, as we all know. So we all can see the formula from the slide. So actually being applied, this 4 being actually being applied to a real published architecture. So 227 minus 11 divided by 4 plus 1 equals 55, matching our 55 by 55 by 96 output. And the number of weights in the first layer alone is 11 times 11 times 11 times 3 times 96, right? So when equals to which is equal to 34,848. So computed exactly the same way we computed the parameter counts back in the previous slide, uh, and just with the AlexNet's actual numbers plugged in, right? So overall AlexNet has 8 layers with the learnable weights. So 5 convolutional and the 3 fully connected, which was considered very deep for 2012 and was only made trainable because of the GPU acceleration. So it's worth appreciating just how much of hardware and engineering achievement this was at the time. So training a network this large on a data set as big as the ImageNet was simply not feasible on the CPUs available before GPUs were repurposed for this kind of massively parallel computation. And this is a part of why AlexNet is remembered as a milestone. It was not just a clever architecture, right? So it was a proof that the combination of the right architecture, enough data, and the enough compute could unlock dramatically better performance than anyone had achieved before. So this is what is the advantage of AlexNet. And this is how the AlexNet is famous for. Then moving ahead, we'll see the techniques used in the AlexNet. So we have the techniques AlexNet has introduced. Let's see one by one. So AlexNet just did not prove depth work. It introduced the several specific techniques still used today, and it's worth understanding the reasoning behind each one and not just its name. So ReLU activation, it's the first part. It defined as the maximum of 0 to x, replace the older sigmoid and tanh function. To understand why this mattered so much, because let's just think about what the sigmoid and tanh do. So for large positive or large negative inputs, both functions flattened out almost completely, meaning their gradient, their slope becomes very close to zero in other regions. So this is called saturation, and it's a major cause of the vanishing gradient problem we discussed earlier, right? So because during the backpropagation, these near zero gradients get multiplied together across layers and shrink the learning signal reaching early, earlier layers. So ReLU, by contrast, has a constant gradient of exactly 1 for any positive input. No matter how large, it simply never saturates on the positive side. So the gradient signal flows through active neurons without shrinking. So because its gradient doesn't shrink for the active neurons, it trained roughly 6 times faster to the same error layer, which was the dramatic practical improvement. Right. Then we have the dropout. This dropout randomly zeroes out a fraction of the fully connected neurons during training, which reduces overfitting on those very large fully connected layers. So the intuition here is that if a neuron can't rely on any specific set of other neurons always being present, since a random subset get dropped every training step. So the neuron is forced to learn more robust, redundant representations rather than fragile ones that depend on the precise cooperation of the specific neurons. So this has a similar effect to training many different smaller networks and averaging them together without the cost of actually doing so. Then we have the data augmentation. So random crops and the horizontal flips of the training images. So artificially expands the training data sets and improves how well the model generalizes because it exposes the network to many slightly different versions of the same underlying object. Teaching it that small shifts, crops, or the minor flips of an image shouldn't change the predicted class. And then we have the local response normalization, which normalizes the activation across nearby channels, encouraging the competition between the filters. So the idea being that if one filter responds very strongly to a pattern at the given location, nearby filters responses at that same location get suppressed somehow. So sharpening the network selectivity. So this was later replaced by more effective batch normalization in a newer architectures. So which normalizes across the batch dimension instead and has proven more consistently helpful. And then finally, we have multi-GPU training. The network was literally split across the GPUs, which was necessary simply because of the memory limitations of the hardware available in 2012. So a single GPU at this time simply didn't have enough memory to hold the entire network. So the authors split the filters across two GPUs with limited communication between them at certain layers as a practical engineering workaround. So this was all about the techniques which have been used in the AlexNet. Now we'll see like where the AlexNet's parameters really live, right? So this was one of the most important because it connects directly back to the parameter counting exercise. So which we did on the previous slides also. So AlexNet has roughly 60 to 62 million parameters in total. Now look at this bar comparison. So we have this convolution one with its 11 by 11 filters uses only 34,848 weights, barely visible on this scale. But HC1 going from the flattened 9,216 values to 4,096 units uses 37 lakhs, 3 crore 77 lakhs 48,736 weights on its own. That's such a huge number we can see. And then we have HC2 from 4,096 to 4,096 uses again same in the crores weights. And HC3, the final output layer uses 40,000, 40 lakhs 96,000 weights. So add up these three fully connected layers and we get about 58.6 million weights. So roughly 98% of AlexNet's entire parameter count, even though it's the convolution layers that are doing the actual visual feature extraction. Now we'll see why does this matter beyond just being a curious statistics, right? The reason is it has a real consequences. So those 58 million plus fully connected beds are a major reason AlexNet needed dropout so badly in the first place. A layer with that many parameters trained on the final dataset is highly prone to overfitting, essentially memorizing quirks of the training data rather than learning generalizable patterns. It also meant AlexNet model size and the memory footprint were dominated by layers that, in some sense, were not doing the interesting visual reasoning work at all. So this is exactly the same imbalance we saw earlier in our small worked examples, right? So just as much a larger scale, fine. Then so our researchers understood exactly where these AlexNet parameters were being spent, and they knew exactly what to target for the improvement. So that's the conclusion of this parameters slide of this AlexNet. Let's move ahead and see the limitation of AlexNet and what evolved next after that. So what were the AlexNet's actual limitation? What come after to fix them? This is where all the concepts of our lectures are engrossed together. Correct? Our inherent story. So first, the huge fully connected parameter count, about 58 million of roughly 60 million total, was addressed by GoogleNet's use of the global average pooling instead of the large FC layers. So remember from the previous slides that global average pooling collapses each entire feature map down to one number per channel. So by using this instead of flattening and feeding into a massive dense layer, GoogleNet was able to drastically cut its parameter count while remaining just as deep or the deeper than AlexNet. Then the second large first layer filters, that is 11 by 11, costing 34,484 weights just for the one layer, were addressed by the VGDNet, which shows that stacking multiple smaller 3 by 3 filter achieves the same receptive field far more efficiently. So two stacked 3 by 3 convolutions have the same receptive field as one 5 by 5 convolution, but with fewer total weights and importantly is with an extra non-linearity in between. Right? So then thirdly, we have the AlexNet used a fixed filter size at each layer with no multi-scale processing. Right? So every neuron at a given layer looked at the same size window of the input. We have this GoogleNet's inception model fix this by running several filter sizes like 1 by 1, 3 by 3, 5 by 5 in parallel within the same layer and concatenating their outputs. So letting the network capture the patterns at multiple scales simultaneously rather than committing to one fixed scale per layer. Then fourth one, the AlexNet had no skip connections and being only 8 layers deep, going much deeper by naive stacking runs into the vanishing gradient problem, which we have discussed previously. Correct? So we would have been essentially possible with this AlexNet build, so purely the sequential design. Then we have the evolution chain, correct? The evolution chain, what we have seen till now. So it is like a summary. So let's tie the entire lecture, entire like unit two together as one connected chain. So which is also the great structure for us to understand by now. So every single link in this chain should carry the real conceptual weight. So a plain ANN on the raw pixels means over 150 million weights because flattening destroys the spatial structures and forces every pixel to connect to every neuron. So convolution cuts this down to about 27 weights per filter by exploiting the fact that useful visual patterns are local and can be detected with this small sliding window. So parameter sharing then gives us a roughly 9,600 times a reduction on the top of that by reusing the same filter weights everywhere instead of learning separate weights per position. So this combination produces the equivalence. The output shifts currently when the input shifts, but not invariance, meaning the network still cares exactly where the feature is. So pooling fixes that gap at the cost of discarding three out of every four values. It processes by summarizing the local neighborhoods down to their strongest response. The variance of the convolution then fix the convolution's own remaining cost. So padding fixes border and shrinkage issues, and striding and dilation fix receptive field and downsampling cost. And depth-wise separable. One by one convolution fix raw conceptual computational cost, right? And then finally, the AlexNet proves this entire approach works at a real scale. And so exposing exactly the inefficiencies like its FC layer parameter dominance and its lack of multi-scale processing or the skip connections that motivated everything that came after it. So this was all about the convolution neural network and the end part of the AlexNet. So I hope if there are any questions, you have understood all this. I hope you have understood the unit two. And if you have any questions, you can ask now.